Hi, good day. I'm Engineer McFarland. I'll be discussing fluid mechanics. So if we say fluid, it's either liquid or gas. So let us discuss the basics. So let's have the fundamental properties. So what are the fundamental properties of fluids? In civil engineering board exam, we have the three most common. Okay, the first one is the gamma, or the unit weight. That is basically equal to the weight divided by the volume. We have the rho, or the density. This is the mass divided by the volume. Tapos specific gravity, this is the unit weight of any object divided by the unit weight of water. Or pwede rin, the density of any object or any matter divided by the density of water. As you can see, our universal reference is water. So we should know the constants of water. So unit weight of water is 9,810 newtons per cubic meter. We can have it as 9.81 kilonewtons per cubic meter. English unit, this is 62.4, okay, the pound force per cubic foot. So whichever is useful. Then we have the density of water is 1,000 kilograms per cubic meter, or we can have it as the 1 gram per cubic centimeter. English unit, this is 62.4 divided by acceleration due to gravity in English, 32.2. So this will give a value of 1.938. This will be pound mass, a pound mass per cubic foot. So pound mass is also known as the slugs. This is the slugs per cubic foot. And most of the time, they are not given. The acceleration due to gravity is 9.81 meters per second squared, 32.2 feet per second squared. So these constants are not given. So again, they are constants. We should memorize them. Alright, so let's have a sample problem for the fundamental properties of fluids. So this is a past board exam in civil engineering for fundamental properties. Alright, we have our first example for number 1. So glycerin having a volume of 0.452 cubic meter weighs 5,587 newtons. Number 1, what is the unit weight of the glycerin? So basically, unit weight is the weight divided by the volume. So what is the given weight? 5,587 newtons. Divided by the volume, this is 0.452 cubic meter. All we have to do is observe the unit. You can survive this question by simply unit analysis. So 1,000 newtons is the same as 1 kilonewtons. 1 kilonewton. So that we can cancel the Newton unit. So this is equal to 5,587 divided by 0.452 divided by 1,000. So we have that value as 12.361. This is now in terms of the kilonewtons per cubic meter. So that is letter D for number 1. Then number 2, what is the density of the glycerin? Density is basically equal to the mass divided by the volume. We don't have the mass, but we can convert the weight into mass. This is equal to 5,587 newtons divided by the volume 0.452 cubic meter. The required unit is kilograms per cubic meter. 1 kilogram is the same as 9.81 newtons. So cancelling the Newton unit, the remaining unit will be obviously kilograms per cubic meter. 5,587 divided by 0.452 divided by 9.81. And we'll be having a value of 1,260. Remaining units, the kilograms per cubic meter. That is letter A. Then we have number 3, specific gravity. So we can have it as in terms of the gamma, the unit weight of any object divided by the unit weight of water. So the unit weight of the glycerin is 12.361 kilonewtons per cubic meter. Take note that specific gravity is unitless. So therefore, we are using the gamma water having the same unit as kilonewtons per cubic meter, the 9.81 kilonewtons per cubic meter, so that we can cancel the units. And this is now equal to 1.26. Then we can also have the specific gravity in terms of the rho. So this is the density of any object divided by the density of water. So if we are using the density of the glycerin, that is 1,260 kilograms per cubic meter. Density of water having the same unit is the 1,000 kilograms per cubic meter. So that we can cancel the units. This is the same as 1.26. We can have this specific gravity in terms of gamma and the rho. So this is a sample problem in our board exam. We can consider them as easy problems or appetizer problem. So we proceed to pressure. So we have pressure absolute is equal to, this is the pressure gauge, plus the pressure atmospheric or the PATM. In problem solving, the pressure gauge is simply equal to the unit weight of the fluid times its corresponding height or corresponding depth. We have PATM or the atmospheric pressure. If not given, we are to use constants. That is 101.325 kilopascals, or in English unit, this is 14.7 pounds per square inch, or I also express in terms of the height of mercury, that is 760 millimeters of mercury. So take note, these pressures are at sea level. If not given, we are to use this constants. So let's have this sample problem. Problem number 4. So in the figure shown, if the atmospheric pressure is equal to 101.03 kilopascals and the absolute pressure at the bottom of the open tank is 231.3 kilopascals, what is the specific gravity of the liquid? So here, at the bottom of the tank, we have the value of the absolute pressure equal to 231.3 kilopascals. So these layers of liquids will give us the value of the pressure gauge. So how do we compute for pressure gauge? That is the gamma unit weight times height. But if we have layers of liquids, basically all we have to do is summation, the summation of gamma H. And the air pressure will give us PATM. Take note, there's a given value, so we are to use that value. We are not using the constant. Go back to our equation. So we have P absolute is equal to the pressure gauge plus the pressure atmospheric. So we have that value as 231.3 is equal to the pressure gauge plus the atmospheric pressure is given as 101.03 kilopascals. So let's have the equivalent of the pressure gauge. That is the same as 231.3 minus 101.03. We have the value equal to 130.27 kilopascals. So we have the pressure gauge is equal to the summation of gamma H. So let us just recall what is the equivalent of the specific gravity. So specific gravity is equal to the unit weight of any object divided by the unit weight of water. We can have the unit weight of that object as the specific gravity multiplied by the gamma water. So since the specific gravities are given, so we have the pressure gauge is equal to 130.27 27 equal to, the first layer, specific gravity is 0.89 multiplied by gamma water, 9.81. Okay, its height is 1.5 plus the next layer is simply water. Specific gravity is equal to 1. That is 9.81. Its corresponding height is 2.5 meters. Okay, then plus the unknown liquid, that is its specific gravity S, multiplied by gamma water, that is 9.81. Its height is equal to 2.9 meters. Then plus the last layer, this is 13.6, that is mercury. Times 9.81, its height is 0.4. So as you can see in this equation, the only unknown is the specific gravity. So let us compute for the specific gravity. We can use shift solve. That is 130.27 is equal to 0.89 multiplied by 9.81 times 1.5 plus 9.81 times 2.5 plus the alpha x for the unknown specific gravity times 9.81 multiplied by 2.9 plus 13.6 times 9.81. Its corresponding height is 0.4. Shift solve. So we have an answer of 1.38. That will be the specific gravity of the unknown liquid. We know that as we go deeper, the specific gravity increases. So our answer should be between 1 and 13.6. So as you can see in our choices. So our answer will be 1.38. So our next topic is hydrostatic force, or this is the force acting on submerged surfaces. So let's say we have this rectangular section that is submerged in liquid, having the condition the pressure on the surface is equal to 0. Let's say the dimension is having a width b and a depth d. So the width b is perpendicular to the paper. So we know from the concept of pressure, as the depth increases, the pressure increases. So let's say the pressure increases as the depth increases. So this is the pressure diagram acting on the surface. So what will be the magnitude of the pressure at this point? So that is equal to gamma h. Let's say this is the unit weight times the depth of the rectangular section. So how do we compute for the magnitude of the hydrostatic force? Hydrostatic force. So hydrostatic force is basically equal to the volume of the pressure prism. That is equal to the volume of the pressure prism acting on this submerged surface. If we are to compute for the volume, this is a triangular prism. So that is 1/2. What is our base? So basically the base is the unit weight of the liquid times d. What is the height? The height is d. Then multiplied by that is the area. To be volume, we are to multiply it to the width perpendicular to the paper, that is b. If we are to conclude, what is b times d? B times d is basically equal to the area. So we will be having the equivalent of the hydrostatic force as the unit weight of the liquid. Then we have the depth divided by 2, then multiplied by the area. So what is depth over 2? Depth over 2, this is that distance from the liquid surface to the mid-height of the submerged surface. This is the d over 2. So we call it as the h bar. Okay? So d over 2 is basically equal to h bar. So we can have our general equation for the hydrostatic force as the unit weight of the liquid. This is multiplied by the bar h or h bar multiplied by the area of the submerged surface. So this is the general formula. So take note that, what is the definition of h bar or bar h? This is a distance from the location of zero pressure. So take note, this formula is only applicable if the pressure on the surface is equal to 0 to, what is this point? If d over 2 for a rectangular portion, that is basically the center of gravity. So bar h is the distance from the zero pressure to the center of gravity of a given of a submerged surface. So if the pressure on the surface is not equal to 0, take note that this is not applicable. Then, what is the location of the point of action of the total hydrostatic force? So the total hydrostatic force will not be acting on the center of gravity. It will be acting on the center of pressure. So this will be your hydrostatic force. What is the distance from the center of gravity to the center of pressure? This is E. So what is E? This is the eccentricity. So how do we compute for the eccentricity for vertical surfaces? So this is for vertical surfaces only. That is, eccentricity is equal to the moment of inertia of the submerged surface divided by the area multiplied by the bar h. This is our formula for eccentricity. So let's have an example. So let's have this problem. This is a past board exam problem. A 3.5 meter square plate is immersed in water in a vertical position such that the two edges of the square are horizontal. So this is the submerged surface, 3.5 meters by 3.5 meters. The immersion is such that the center of pressure in the plate is 12 centimeters from the center of gravity. So let's say this is the center of gravity. Then we have the center of pressure. So the distance between these 2 points is the eccentricity. And according to the problem, the value of the eccentricity is equal to 12 centimeters or equal to 0.12 meter. First requirement, this is a situational problem. So 3 questions. How far below the water surface should the upper part of the plate be submerged? So we are looking for this distance. Let's say this is y sub 1. So there's no indication that we have a pressure on the surface. So this is a zero surface problem. How do we locate that, or how do we compute for this y sub 1? So we are to use that given. So for problem number 5, the given is E. We are using the equation for E, that is equal to the moment of inertia divided by the area multiplied by the bar h. So for a rectangular section or square section, what is the equivalent of the moment of inertia? That is the BD cube divided by 12. So I hope that you can memorize the moment of inertia of any section. So we have the eccentricity is equal to 0.12. This is equal to, the base is 3.5. The depth is also equal to 3.5. This is raised to 3 all over 12. Divided by the area. What is our area? That is a square, 3.5 meters by 3.5 meters. Multiplied by the bar h. So, first thing to compute, una nating mako-compute is yung bar h. So, you have 3.5. You can use ship solve. So we have the computed value of the bar h is equal to 8.507 meters. So what is bar h? That is the distance from the zero pressure to the center of gravity. of the submerged surface. So this is our bar H. Okay, based on this figure, okay, what is this distance, the location of the center of gravity? Since this is a rectangle, that is basically the depth over 2. How do we compute for y sub 1? So y sub 1 is basically equal to the bar H, okay, minus half of the depth. That is the d over 2. So for problem number 5, okay, we have y sub 1 is equal to the computed bar H minus the d over 2. So this is equal to 8.507 minus 3.5 divided by 2. So we have the value of y sub 1. 8.507 minus 3.5 over 2 is equal to, using 3 decimal places, this is 6.757 meters. On our choices, we have only 2 decimal places. We have that as 6.76. Letter A. Okay, then next question. This is number 6. What is the distance of the center of pressure from the water surface? So we have that as the point of action, that is the same as the point of action of the hydrostatic force. This is the point of action of the hydrostatic force on the center of pressure. This is F. We are looking for this distance from the surface of the water to the center of pressure. Let's say this is H sub P. So how do we compute for that value? That is basically equal to the bar H plus, take note this distance is the same as E. So computing for H sub P, that is basically equal to the bar H plus the eccentricity. So we have that as 8.507 plus, given naman yung eccentricity, we have 0.12. So we have our H sub P is now equal to, what is 8.507 plus 0.12, that is equal to 8.627 meters. 8.627 meters, on our choices. 2 decimal places again, that is equal to 8.63. Letter B. Then we have question number 7. For problem number 7, determine the hydrostatic force acting on the plate. How do we compute for the hydrostatic force? That is the force equal to gamma, the bar H multiplied by the area. So more likely this is direct sub na lang tayo. What is the gamma? This is water. We have 9.81 kilonewtons per cubic meter. What is the value of the bar H? Computed as 8.507 meters. Area, this is a square. We have 3.5 multiplied by 3.5. So that will give us a unit of square meters. So if we are to do a unit analysis, this is cubic meter, meter, square meters. So the remaining unit will be kilonewtons since that is a force. So we have the total force is now equal to 9.81 multiplied by 8.507 multiplied by 3.5 squared. We have that value as 1,022.307 kilonewtons. So this will be our answer. On our choices, that is letter A, that is 1,022.3 kilonewtons. So this is our solution for problem 5 to 7. So let's try this problem. This is for item number 8 to 10. Situational problem. The gate AB shown is hinged at A and kept closed by a force P at B. So P air is equal to 18.46 kilopascals vacuum. So that is the pressure of the air inside the tank. Number 8, determine the nearest value of the total force exerted by the oil on the plate. So on our previous examples, Okay, for number 8, how do we compute for the total force exerted by a liquid on submerged surfaces? That is the unit weight, okay, multiplied by the bar H multiplied by the area. But we have a limitation for this formula. So at surface, okay, the pressure should be equal to 0. But as you can see in this problem, okay, the pressure on the surface is not equal to 0. We have a pressure equal to 18.46 kilopascals, and it should be negative. So why is it negative? Also, it is a vacuum pressure. So vacuum pressure is a negative pressure. But okay, so since this formula is no longer applicable, okay, but we can still reinterpret. Okay, so we have basically we have the equivalent of pressure is simply equal to gamma h, or the unit weight times the height. So what do we mean by gamma bar h? Take note that if we say bar h, this is the distance from the liquid surface having a zero pressure to the center of gravity. But bar h is not applicable for this one, for this problem. So therefore, we can rewrite this one. Gamma bar h is the same as gamma h is pressure. Gamma bar h is the pressure down to the center of gravity. So then we can reinterpret this formula as the force is equal to the pressure down to the center of gravity multiplied by the area. So all we have to do first is compute for the pressure on the center of gravity. So let's have a figure, or a larger figure. Okay, so this is our figure. So again, initially, we have the air pressure inside the tank is equal to negative 18.46 kilopascals. So again, it is negative since it is a vacuum pressure. So let us assume that this is the center of gravity of the gate. All we have to do is determine this distance. The distance from the center of gravity of the gate to the surface of the oil. So we know this height, since center of gravity is located at the mid-height for a rectangular section, this is 3 meters. And if this is 7 meters, and this is 6 meters, so 7 minus 6, the remaining height should be equal to 1 meter. So we are considering a height of 4 meters of oil. Okay? Okay, so we can now compute for the pressure down to the center of gravity. We have the pressure on the center of gravity is basically the summation of pressures down to the center of gravity. So we have the initial pressure, that is air pressure, negative 18.46, plus the pressure exerted by the oil. Specific gravity is 0.8, multiplied by gamma water, 9.81. We are considering a height or a depth of 4 meters. So pressure on the center of gravity is equal to negative 18.46, plus 0.8 of 9.81 multiplied by 4. So this pressure is equal to 12.932 kilopascals. So computing for the force, if gamma bar h area is not applicable, is the pressure on the center of gravity multiplied by the area. We have the force is now equal to 12.932. So kilopascals is the same as kilonewtons per square meter multiplied by the area of the gate. So the area of the gate is 2 by 6. 2 meters by 6 meters. So this is in terms of the square meter. Unit analysis, cancelling square meter. The remaining unit is kilonewtons. So 12.932 times 2 times 6 is now equal to 155.184 kilonewtons. So this will be our answer for problem number 8. If we are to check on our choices, so 155.184, the closest value is letter B, that is 155.18 kilonewtons. The next item, item number 9. Compute the value of the location of the total force from A. So let's have another figure. This is for problem number 9. Okay, for problem number 9, we are looking for the location of the force from A. So we know that the total force is not acting on the center of gravity. Okay, it is acting on the center of pressure. So this is, we assume this is the point of action of the force. Okay, that is on the center of pressure. And the distance from the center of pressure to the center of gravity is the eccentricity. Okay, then if this is point A, that is the upper portion of the gate, we know that this is the center of gravity, mid-height, that is 3 meters. So let's say we are looking for this distance. Let's say y sub p, the distance of the force from point A. What is the equivalent of y sub p? Y sub p is equal to 3 meters plus the eccentricity. How do we compute for eccentricity? That is the moment of inertia divided by the area multiplied by the bar h. But again, we don't have the value of the bar h. So how do we compute for that? Let us just reinterpret the equivalent of the force. So basically, we have force is equal to the unit weight of the liquid bar h multiplied by the area. So we have the equivalent of the force is equal to 155.184 equal to gamma. What is the gamma of the liquid? Specific gravity 0.8 times 9.81 multiplied by the bar h multiplied by the area of the gate. This is 2 meters by 6 meters. So computing for the bar h, 155.184 divided by 0.8 by 9.81 divided by the area, that is 2 by 6. So we have the equivalent of the bar h is equal to 1.648 meters. But this is just an equivalent bar h. It is not existing on our actual problem. So we have now the bar h. We can now compute for the eccentricity. What is the moment of inertia of a rectangular section? So we have I is equal to the base, the depth cube divided by 12. So we have a base of 2 meters, a depth of 6 cube. This is divided by 12 all over. Area is 2 by 6. I computed bar h is equal to 1.648. So computing for the eccentricity, we have 2 times 6 cube divided by 12. Divided by 2 or divided by the area, divided by 6, then divided by bar h, 1.648. So we'll be having a value of the eccentricity as 1.820 meters. So computing for the y sub p, this distance, that is 3 meters plus the eccentricity 1.820. We have y sub p is equal to 4.820 meters. So this will be our answer for problem number 9. If you are to check on our choices, for problem number 9, 4.820, we have letter A, that is equal to 4.82. And then item number 10, which of the following gives the value of the force P needed to keep the gate closed? So let's have another clean figure. This is for item number 10. So this time we are now looking for the value of this force, the force P. How do we compute for that one? Earlier we are able to compute for this required. We compute for the value of force F, and it's a distance from point A, which is the y sub P. we are just to apply mechanics. We can do summation moment at A equal to 0, okay, clockwise moments to be positive. So the clockwise moment is that force P multiplied by how far is force P from A? That is 6 meters, the height of the gate, minus the force multiplied by the y sub P is equal to 0. All we have to do is substitute. So we have the force P multiplied by 6 minus the force F. That is the 155.184. Y sub P is 4.820 meters equal to 0. We have the force P at B. That is the force P at B. 155.184 multiplied by 4.820 or 4.82. This is divided by 6. So we'll be having that force as 124.664 kilo Newton. So this will be our answer for item number 10. If you are to check on our choices, for item number 10, the closest value is, the computed value is 124.664, but on our choices, the closest value is 164.68. Maybe we use a different number of decimal places. So by the way, when it comes to situational problems, especially on hydraulics and geotechnical engineering, usually the required on problem on the first few problems or first two questions will be used on the last question. That is common when it comes to situational problem. As you can see, what is our last equation? We do the summation moment about point A. That is the force P multiplied by 6 minus the force F multiplied by the y sub P equal to 0. So force F is required on item number 8. Y sub P is item number 9 and force P is item number 10. If you have this situation, you can do trial and error, okay, as a way of survival for board exam. Okay, so let's have another problem.
Okay, so let us discuss dam. So to start the analysis, usually we are to consider what are the forces involved. So first, usually for gravity dam, we are just considering its self-weight. And if there are no more other vertical forces, we can consider this as the vertical force. In some references, we're using the R sub Y. We are also to consider the hydrostatic force exerted by the retained water. Most of the time, it's water. Exerted by the retained water. So let's say this is the hydrostatic force. How do we compute for hydrostatic force? That is the gamma bar H times the area. Then, if this side contains the water or retains the water, and on the right side we don't have a water, or for example we have water but lower in level, we are considering this point of the base of the dam as the heel, and this point is the toe of the dam. Okay, then we have a conservative analysis for dam. In the conservative analysis, we are just considering 1 meter strip. Okay, so this is just a 1 meter strip. So let's say B as the width of the base. So if we are to do summation forces vertical, I will be having a reaction at the base also equal to the weight of the dam, or the same as the Ry. Let's say this is the center of gravity of the base. So obviously that is half of the base width. So let's say this is B over 2. So usually the reaction Ry is not acting on the center of gravity of the base. Okay, let's say if it is at a distance x from the toe, it will result to an eccentricity at the base, and it will result to a moment. So what will be the value of that moment? The moment is equal to Ry multiplied by the eccentricity. Okay, so how do we analyze or for example, we are to compute for the pressure at the base, the pressure at the base of the dam. Let us recall the combined stress from our strength of materials. So we are using sigma in strength of materials. That is the force divided by the area. This is positive or negative force over area, plus or minus the bending stress, the MC over I. So this is the combined stress, axial plus bending. But here in fluid mechanics, we are using P for pressure instead of stress. Then the force is equal to Ry divided by the area. Our area is, that is the width B times 1 meter strip. This is the width of the base of the dam, B multiplied by 1 meter strip. Then we are assuming that it is under compression since the dam is the weight of the dam is obviously downward, and we are using positive sign, which means compression is good for the soil, since we don't have a tensile property for the soil at the base of the dam. Okay, then plus or minus MC, what is our moment? Okay, the moment is equal to Ry times the eccentricity. This is Ry times E. Then what is the value of C? Okay, the value of C is the distance from the edge of the base to the center of gravity. This will be our C. That is basically the B over 2. Then divided by the moment of inertia, this is our orientation for the moment. So our base or the width of our beam, if we are to analyze it as a beam, is 1 meter with a depth of base width B. This is raised to 3 divided by 12. The moment of inertia of a rectangular section. So we have now the pressure at the base is now equal to Ry divided by B plus or minus. So we are cancelling one of the base. So this will be B squared. Then we bring this 12 in the numerator. That will be 12 divided by 2. That will be equal to 6. This is 6 times Ry times the eccentricity. This is divided by B squared. So from this equation, we can factor out Ry over B. So the pressure at the base is now equal to, factor out Ry over B. This is now multiplied by 1 plus or minus the 6 times E divided by B. So this is our general equation for the computation of the pressure at the base of the dam. So obviously, we are using the addition operation if we are computing for the maximum pressure, and we are using the minus operation if we are computing for the minimum pressure. So the question is, when do we know if the hill is experiencing a maximum pressure? So let's say this is the 1 meter strip base. This is the hill. So let's say this is the center of gravity of the base. If the reaction is closer to the hill, which means the concentration of the weight is near the hill, and we can conclude that the maximum pressure is basically the pressure on the hill. But in some cases, or most of the time, or in most cases, for example, again, this is the 1 meter strip. Our reference point is the center of gravity. For example, that the reaction at the base is near the toe. It is closer to the toe compared to the heel, which means the concentration of the weight is near the toe, and we can conclude that the maximum pressure will be equal to the pressure at the toe. And if Ry again is closer to the toe, we can conclude that the pressure at the heel is the pressure minimum, or on our previous figure. So if P max is equal to the pressure on the heel, that then we can conclude that the pressure on the toe, is equal to the pressure minimum. Alright, so that's how we compute for the pressure maximum and pressure minimum, or how do we compute for the pressure at the toe or the pressure at the heel. So it depends on the location of the reaction of the base. So this is our general formula for the computation at the pressure at the base of a dam. So let's have an example. So let's have this example. A dam is triangular in cross-section with the upstream face vertical. Water is flush with the top. The dam is 8 meters high and 6 meters wide at the base and weighs 2.4 tons per cubic meter. The coefficient of friction between the base and the foundation is 0.8. Number 11, I determine the unit pressure at the toe. So let's have first the given. So the given, one of the given is the density of the concrete. That is, let's say raw concrete is equal to 2.4 tons per cubic meter. Or this is the same as 2,400 kilograms per cubic meter. Since 1 metric ton is basically equal to 1,000 kg. So if we are to determine the specific gravity of the concrete, that is the density of the concrete divided by the density of water. So this is equal to 2,400 kilograms per cubic meter divided by the density of water is 1,000 kilograms per cubic meter. We'll be having a density of 2.4. So this is our dam. It is 6 meters wide at the base, 8 meters high. So the height of water is the same as the height of the dam. So what are the forces that are we going to consider? So we have first one is the weight of the dam. Since we don't have any vertical force, that is our net vertical force Ry. How do we compute for the weight? So if you are to recall, unit weight is equal to the weight divided by the volume. So we'll be having the weight as equal to the unit weight of the concrete multiplied by the volume. Take note, kindly imagine that we have a dam 1 meter perpendicular to the paper, since we are considering 1 meter strip. So we have the weight. How do we have the gamma concrete? We are using its specific gravity 2.4 multiplied by 9.81 gamma water, 9.81 kilonewtons per cubic meter. Then multiplied by the area of the dam, that is 1/2, 6 meters at the base, 8 meters high, and we are considering 1 meter strip for the unit to be in cubic meter. So canceling cubic meter. So since this is a weight, we'll be having a unit of kilonewtons. That is 2.4 times 9.81 multiplied by 1/2 of 6 times 8. Times 1 meter strip. So it's the same as 500. We have a value of 565.056 kilonewtons. Okay, so this is the weight of the dam per 1 meter strip. Okay, conservative analysis, 1 meter strip. Okay, other than the weight of the dam, we are also to consider the hydrostatic force. That is the force exerted by the retained water. So how do we compute for the hydrostatic force last time? So basically we have hydrostatic force. Hydrostatic force is equal to the gamma water times bar H multiplied by the area. So kindly imagine we have a vertical wall that is 1 meter wide and 8 meters high. So its center of gravity is obviously at a depth of 4 meters. So we're having the force, or the hydrostatic force. Gamma water is 9.81. Our bar H is simply the the mid height of the dam, that is 4 meters. What is the area under consideration? That is 1 meter strip, okay, multiplied by a height of 8 meters. So that is our total area. So we have the hydrostatic force is now equal to, that is 9.81 multiplied by 4 multiplied by 1 times 8. So we have the force is equal to 313.92 kilonewtons. So this is the force exerted by the water. Okay, so we have now the value of the force and the weight. So by the way, since this is a triangular loading, if we are to locate this one, this force, for triangular loading, that is basically 1/3, 2/3. So this is 2/3 of the height, 8 meters, while this one is 1/3 of 8 meters. Since for triangular loading. Now, if we are to do summation of forces vertical, we'll be having the reaction at the base basically equal to Ry. So let's say this is the 1 meter strip. Okay, we need to locate the reaction at the base. So we have this as Ry. If this Ry is equal to 565.056 kilonewtons. So basically, if we are to do summation forces vertical, this Ry is also equal to 565.056 kilonewtons. All we have to do is locate this value from the toe. So let's say that distance is at a distance of x. So this is the toe of the dam, and this point will be the heel. So how do we locate this reaction at the base? So for problem solving for dam, usually we are doing summation moment at the toe equal to 0, a clockwise moments to be positive, just to locate this reaction. So what are the clockwise moments? So one of the clockwise moment is this reaction that is equal to 565.056, that is at a distance x from the toe. Then plus the hydrostatic force is also counterclockwise. This force, the value is equal to 313.92. What is its distance? How far above the toe? That is 1/3 of the height of the dam. We have 1/3 of 8 minus the only counterclockwise moment is the self-weight of the dam. This one. So what is its location? So again, this is a triangular section. So basically, this distance is 2/3 of 6. 2/3 of the base, 6 meters. So that is minus 565.056 multiplied by 2/3 of 6 meters. And this is now equal to 0. So let us compute for the value of x. How far is the reaction at the base from the toe? You may use ship solve. So we have the value of x equal to 2.519 meters. Now, if you are to analyze the base of the dam, so we have the base of the dam is equal to 6 meters. So if we are to locate its center of gravity, obviously that is mid-length. So this is 3 meters. This is also 3 meters. But okay, the computed location of the Ry, so let's say this is the reaction of the base, okay, at a distance x. Okay, what is the computed value of x? That is equal to 2.519 meters. Okay, 2.519 meters. So it results to an eccentricity E. Okay, how do we compute for that one? And basically, the location of the reaction at the base is closer to the toe. That makes the pressure maximum is the pressure at the toe, since the concentration of the weight at the base is closer to the toe. And that also makes that the pressure at the heel is the pressure minimum. How do we compute for the eccentricity based on the figure? So eccentricity is equal to this distance, 3 meters, mid-length of the base, minus the computed value of x. So 3 minus x. We have the eccentricity is now equal to, this is 3 minus 2.519 meters. Eccentricity is now equal to 3 minus 2.519. Is equal to 0.481 meter. Okay, so required is the pressure at the toe. So the pressure at the toe, based on the location of the reaction at the base, is basically equal to the pressure maximum. How do we compute for the pressure? That's equal to Ry divided by the base width. This is multiplied by 1 plus or minus 6 times the E divided by the base. But again, if we are computing for the maximum, we have to use addition. Okay, so we have the pressure at the toe. Okay, the pressure at the toe is now equal to Ry. That is equal to 565.056 divided by the width of the dam, base width, that is 6 meters. Supposedly, this is multiplied by the 1 meter strip. This is kilonewtons. Multiplied by 1 maximum plus 6 times eccentricity 0.481 divided by the base width, also 6 meters. So we have the pressure at the toe. For this problem is the pressure maximum is equal to 565.056 divided by 6, multiplied by 1 plus 6 times eccentricity, 0.481, divided by 6. That's equal to, computed value is equal to 139.475 kilonewtons per square meter. If you are to observe the units, this is kilonewtons, meter, that is kilo pascals. Kilonewton per square meters is kilopascals. Now our choices. On the choices we have, the closest value is 100. This is equal to 139.4 kilo pascals. Then number 12. Question number 12. Determine the factor of safety against overturning. So we have for number 12, how do we compute for the factor of safety? The factor of safety for overturning, this is, let's say, F S for overturning is simply equal to the summation of the resisting moments or righting moments divided by the overturning moments. So basically, if we say righting moment, these are the moments that will keep the dam in position. While overturning moment, so again, righting moment or resisting moments, so these are the moments that will keep the dam in position. Then overturning moments, these are the moments that will make the dam fail. So if we are to observe, okay, the resisting moments or the righting moment is basically caused by its weight. Okay. Okay, and most of the time when it comes to gravity dam, okay, the weight will give a righting moment, and most of the time, the force that will give an overturning moment is basically the force exerted by the retained water. So we will be having, for this case, we have one righting moment or resisting moment, and we have one overturning moment. Take note that the moment caused by the reaction will not be included. So we have the factor of safety against overturning is equal to 565.056 multiplied by 2 over 3 of 6. So that is the righting moment, okay, due to the weight of the dam. Okay, this is all over. The overturning moment is caused by the hydrostatic force caused by the water, 313.92, okay, multiplied by 1/3 of 8. So we're having a factor of safety against overturning is equal to 565.056 multiplied by 2 over 3 of 6. This is divided by overturning 313.92 multiplied by 1/3 of 8. So we have a factor of safety against overturning equal to 2.7. So again, what are the moments that will keep the dam in position? Usually that is the moment caused by this self-weight. Okay, caused by the self-weight. And if this is our orientation for the dam, usually they are the counterclockwise. Okay. Then, what is the force that will make the dam fail? This is the hydrostatic force. And if this is the orientation of the dam, usually overturning moments are the clockwise moments. So clockwise moments are usually overturning, and counterclockwise moments are usually righting or resisting moments. Okay, so we have 2.7 for problem number 12. That is on our choices, that's equal to 2.7. It's 2.7. And lastly, number 13, I determine the factor of safety against sliding. How do we compute for the factor of safety against sliding? This is for problem number 13. Okay, for problem number 13, so what is the factor of safety? So this is against sliding. We have the factor of safety against sliding is simply equal to mu, that is the coefficient of friction, multiplied by the summation of forces, or the net vertical force, let's say summation of forces along y, divided by the summation of forces along x. So as you can see, in this problem, what is the given value of mu, or the coefficient of friction? The coefficient of friction is given as 0.8. That is 0. We have 0.8. What is the summation forces vertical? We have only one vertical force, that is the Ry. Okay, this is the same as the Ry, while Fx is simply the hydrostatic force. So our Ry is equal to 565.056, divided by the only horizontal force is the hydrostatic force exerted by the water. That's 313.92. We have the factor of safety against sliding is equal to, we have 0.8 multiplied by 565.056 This is divided by 313.92. So we have a factor of safety equal to 1.44. So let us check on our choices. The factor of safety against sliding is 1.44, letter A. So this will be our solutions.